All right, let's get right into it. We're going to tackle a pretty wild idea today. What if the quantum world, with all its weirdness and fuzziness, isn't the bedrock of reality? What if it's actually more like a glitch, a predictable error in how the universe gets read into existence?
To really get our heads around this, let's start with something we all know: digital music. That sound wave coming from a guitar? It's not recorded continuously. Nope. Instead, a computer takes thousands of little snapshots, or samples of it every single second. Then your brain, or your headphones, stitches those samples back together into what you hear as music.
Now here's the catch, and it's a big one. If you sample super fast, you get a perfect reconstruction of the sound. It's a clean signal. But if you don't sample fast enough for how complex the sound is, you get errors. It's a phenomenon called aliasing. You literally create phantom frequencies and distortions that were never in the original sound. You get a glitchy signal.
So, how do audio engineers get around this problem? Well, they don't mess around, they use brute force. They massively oversample, they take way more snapshots per second than they technically need. This huge amount of extra data just drowns out any potential glitches and makes sure the final sound is crystal clear.
Okay, and here's the leap. This is where we go from your headphones to the entire cosmos. What if reality itself is being sampled into existence? What if there's some kind of master clock ticking away, building our universe from a raw underlying signal? And the really big question is, what happens in the places where that signal is undersampled?
So how in the world could this work for the entire universe? To answer that, we got to look at the proposed machinery. An idea called scale-time theory suggests there really is a kind of master clock, an absolute sampler for all of reality. In this image right here, this gets to the very heart of the idea. The theory says this master clock isn't just a point in space, it's a very specific boundary. It's a critical location called the present scale ring. This is ground zero. It's where the raw information of reality first gets processed.
So what exactly is the present scale ring? Well, you can think of it as the place with the fastest possible sampling rate in the whole system. It's the ultimate processor. And because it's the place where information is first resolved, it defines a unique present moment for the entire universe. It's the absolute now.
Okay, so how do we get from a sampling ring to, well, everything we see? The theory paints a pretty cool picture. Imagine so much information trying to get processed at this ring that it creates a cosmic traffic jam. The system is totally overwhelmed. So to handle this insane data overload, the theory says the process is forced to fold into a more complex, higher-order structure, creating new dimensions. And out of that jam, out of that fold, boom, our familiar 3D space and one dimension of time are born.
Right, so if the ring creates space-time, where does quantum mechanics come in? This is where it all clicks back to our audio analogy. The theory's big claim is that the quantum world is nothing more than the region of reality that is being fundamentally undersampled. It's the aliasing zone.
To really get this, we need one key idea: the oversampling ratio, or OSR. It sounds technical, but it's super simple. It's just the speed of the master clock at the ring divided by the speed of some local system's internal clock. It basically tells you how many master ticks happen for every one local tick.
And this ratio, this is everything. In the quantum zone, really close to the ring, local clocks are ticking super fast, so the OSR is low. There just aren't enough master samples to figure out what's going on. The result? You get an ambiguous, aliased signal. But way out here, far from the ring, in our classical world, local clocks have slowed way down. The OSR is gigantic, and that massive oversampling creates stable, predictable patterns. And suddenly, all that famous quantum weirdness starts to look a lot like predictable sampling glitches. Superposition? Well, that's just like having a bunch of different sounds that are so undersampled they produce the exact same glitchy output. The uncertainty principle? Ask any signal engineer, there's always a trade-off between how well you know time and how well you know frequency. And wave-particle duality? That could just be the very same process looking different depending on whether you measure it in a low OSR or high OSR environment.
So how do we get from that glitchy, fuzzy quantum signal to the solid, predictable world that we all live in? The answer is exactly the same one audio engineers use. You just massively oversample it.
This quote from the theory just nails the whole idea. Things seem classical and solid to us, not because that crazy quantum dance ever stops. It doesn't. It's because that dance is being sampled with such overwhelming redundancy that all the glitches and ambiguities just get averaged out, leaving behind only stable, solid patterns.
You can actually map out this journey. Right at the ring, the OSR is basically 1. It's pure, raw, unresolved quantum chaos. Then, as you move away, you enter the quantum universe, where everything is dominated by aliasing. The theory points to a place called the pion scale as the first observer scale, where the OSR is finally high enough for stable patterns, like us, to form. And by the time you get to our macro world, the OSR is astronomical. Patterns are effectively frozen into classical objects.
You know, this even gives us a completely different way to think about mass. In this view, mass isn't some fundamental substance. It's a measure of frozen equalization. It's just what we call a system whose internal clock has slowed down so much that it's being massively oversampled by the universe's master clock. From our perspective, its dynamics look totally static.
So let's just step back for a second. If we entertain this idea, what does it actually change? Well, the implications are kind of huge. They touch on everything from the expansion of the universe to why life exists at all. I mean, for starters, the theory suggests the speed of light might not be perfectly constant over cosmic history, which could give us a whole new angle on the Hubble tension problem. It also suggests a universal reason for complexity to emerge. The universe's overall bit rate is changing. And it might even explain sudden bursts in evolution, like the Cambrian explosion, as moments when the universe's sampling rate crossed a critical threshold, allowing brand new, more complex forms of life to become stable. And that leaves us with one last kind of mind-bending question. See, audio engineers use filters to throw away messy information before they sample to avoid glitches. But this theory suggests nature doesn't do that. It just oversamples the whole raw signal. So if our classical reality is the clean, stable, oversampled version, what rich, complex information from that original raw signal got averaged away and was lost forever in the process?
Now, this is obviously a really deep and complex idea, and we've only just scratched the surface here. If you want to dive in and explore the whole theory for yourself, you can check out the source material at scaletimedynamics.com. Thanks so much for joining me for this one.